Welcome to my DB chemistry curriculum. Today we're on lesson 18, structure 1.4.6. We will be discussing Avogadro's law, specifically of combining volumes, stating that equal volumes of all gases measured under the same conditions of temperature and pressure contain equal number of molecules. We'll discuss in detail what that means in a moment. And we should, by the end of this, be able to solve problems including mole ratio of reactants and or products and the volume of gases. So, why do we have this? Well, we already have learned that with solids, we use moles to compare reagents. With liquids, we use a combination of moles and volume, and that creates our concentration. But what about with reactants that are gases? Well, with gases, we just use volume. So you'll notice that we kind of go from moles to moles and volume to volume. So we kind of just have this transition. Now, how does this actually work? Well, Avogadro, the person who created Avogadro's number or figured out what a mole really is the one who actually discovered that we can compare gases specifically if they follow three things. So there are three factors that are applied applied kind of slash affect gases in a container. A container. Those are specifically the volume, the temperature, and the pressure. So those will change how gas specifically work when you put them in a container. So if you have two containers of the same number of particles, let's say we have here argon, and then here, I'm trying to make sure it's the same amount, we have water vapor. If these are the same number of particles, so the same number of moles, N equals N of argon, N of H2O, remembering that we use N to define the number of moles, and it's the same temperature, it's the same pressure, then turns out the volume will be the same as well. We can actually only need three of these to know that the fourth will be the same as well. Uh, so that's basically what Avogadro is saying. It doesn't matter what gas it is. So specifically, the mass of the particles or identity identity of the element does not affect the properties of the gas, affect the behavior of the gas. Heavier gas particles pretty much act almost exactly the same as lighter gas particles. So let's clarify this up with Avogadro's law. Let's actually define it. The actual definition is what we stated in the beginning. Equal volumes of gas at the same temperature and pressure will have the same number of particles. Well, that means it's the same number of moles because remember, moles are just a way of counting. If there's half a dozen moles or half a mole in one container and half a mole in the other, as long as it's the same temperature, pressure, and volume, it all will work the same. What this basically means is that we can use volume of gases, whoops, of gases to compare reagents as we would with moles. So the best way to do this is with an example. So let's look at the synthesis of water vapor. We take hydrogen gas, and there's H2 because hydrogen and oxygen are both diatomic. I'm using state symbols to denote that these are all gases because Avogadro's law only works with gases. And then I'm going to balance this equation out. So two hydrogen plus one oxygen, and I'll actually include the one here, makes two H2O. This could talk about individual molecules. So if we're looking at the actual molecules, I could have two hydrogen molecules, one oxygen molecule, and two H2Os. This is what this reaction says. We could also talk about moles because these coefficients in front actually refer to the number of moles, not necessarily the number of molecules. In which case, we could have 2 moles to 1 mole, and then it's a ratio, makes 2 moles. But because of Avogadro's law, we can actually look at volume. The volume ratio is also 2 to 1 to 2. What that means is that if I took volume in terms of liters, I could say 2 liters of hydrogen gas plus 1 liter of oxygen gas creates 2 liters of water vapor. And this works considering or assuming that we have the same temperature, same temperature and pressure, and the volume is the same. The amount of moles would be the same. So how do we actually use this in practice? Well, let's do a practice problem. All right. So in my practice problem, we have uh, a reaction, ammonia, NH3, decomposes to form a nitrogen gas and hydrogen gas. Specifically, it decomposes with very specific coefficients, which we'll learn how to balance later, but we have a 2 and a 3. So 2 moles of hyd of 2 moles of ammonia decomposes into 1 mole of nitrogen and 3 moles of hydrogen. Or because of Avogadro's law, 2 volume units make 1 volume unit to 3 volume units, and it doesn't matter what the volume unit is. So in our practice problem, we might be given a prompt of what volume of each product is produced when 5.00 decimeters cubed of ammonia decomposes, and ammonia being NH3. So all we have to do is notice that our ratio is 2 to 1 to 3. So if we have 2 ammonia to 1 nitrogen, then that means our nitrogen volume is half because it's 1 to 2 NH3. Therefore, if NH3 is 5.00 decimeters cubed, then nitrogen is going to be 2.50 decimeters cubed. So this is how we use Avogadro's law of combining volumes. We use it just as we would moles. Furthermore, if we look at our hydrogen, we have 3 hydrogen to 2 ammonia. And if we once again have 5.00, then we know that our hydrogen must be 7.50 decimeters cubed. You can really just take this as a ratio and solve for x. Same thing over here. If that helps, you can do that cross multiplication, do whatever you need, but this is basically it. If you want to stick around, I'll show you one more way to do it. Otherwise, that is the end of this. Now, for those sticking around, the other way I like to do it is you start with your base, your given. So this is 5.00 decimeters cubed of NH3. And we use our ratios with the big parentheses. I want to find nitrogen, and I want to get rid of NH3. Now, to figure out what goes in here, I use the ratios. So nitrogen has a ratio of 1, NH3 has a ratio of 2, and so it becomes NH3 is canceled out, decimeter stays, and all I get is 5 over 2 decimeters cubed NH, or sorry, N2. It'll work with hydrogen as well, 5.00 decimeters cubed NH3, big parentheses. I want to get rid of NH3 and I want to convert to H2. And then once again, I use the coefficients, 3 with that H2 and 2 with NH3. Oh, 3, 2. And that becomes 5 times 3 divided by 2. NH3 cancels out, decimeters cubed H2, which these values give me the same ones that we found up here. So with that said, that's everything we have to do. Hope this helps and have a great day.